using PowerPoint is part of my intellectual trajectory. So it didn't feel right not to do it that way. So this is my intellectual trajectory. And a lot of it has to do with, as I think for most people here, with being lucky in the right place in the right time. I was born in Lima, Ohio in 1940. And briefly, I left Lima. In 1943, I went to Chicago and then to Sioux Falls, South Dakota, where my dad was in the Army Air Corps as a medical officer. In 45, we came back to Lima, and I went to the Lima City schools. And then I went in 1958 to the College of Worcester in Ohio, which I'll talk about a little bit later. And then I made a big leap after 2 years to Harvard. And then after 6 years, I came down here to Yale, and that's where I've been. So it's much less dramatic than what many of you have done. I've really admired your trajectories. But actually, my trajectory started, of course, long before I was born. My great-grandparents were born between 1822 and 1855. My maternal ones had started out with their roots in Massachusetts, Connecticut, New York in 1620 to 1650, and then they migrated north up to toward the St. Lawrence and out to the Western Reserve in Ohio, next to the Great Black Swamp. That's three of my mother's ancestors. The other one was Scotch-Irish and was born in Virginia. My paternal grandfathers were more Scotch-Irish, as you can guess from my name, and one of my dad's grandparents was Pennsylvania Dutch, that is German, and the other one was still in Germany in Swabia. I'm the fifth James McBride in my family. But I don't go by James, I go by Michael. And that's the family name of the Swabians. Jonathan Michael was my great-grandfather. But both James Lewis McBride and Jonathan Michael migrated as infants. And then further on, everybody toward the Great Black Swamp, as it turns out. Okay? And these others moved there, and the one who moved to Detroit actually moved back and got married in Vermont. So my grandparents were born either side of the Ohio-Indiana line. My father's on the Indiana side, my mother on the Ohio side, and my mother's father came down to near where I was born. So there's where my parents were born in 1906 and 1913. They didn't move very far either. My father moved out to San Diego briefly in 1931 and back in 1931. He went to San Diego to be a resident at the hospital out there, but there was a surgeon who was very nasty to a nurse, and he let the surgeon know what he thought about that, and very quickly he was looking for another residency. And that residency, the only opening there was, turned out to be in Lima, Ohio, only 70 miles from where he was born. So that's where he came. There's my father and his older brother. I don't know that my dad ever read Burns. I doubt it. But if so, he would have liked this line from A Man's a Man. The honest man, though e'er so poor, is king of men for all that. This is the Scotch-Irish tradition. These guys are Hoosiers. In the David Hackett Fisher's book Albion's Seed, about the 4 British migrations to the U.S. and how they influenced sectional attitudes, he says always the terms crackers, rednecks, Hoosiers, which incidentally were North England terms, they didn't originate in the U.S., but they describe the same paradox of poverty and pride. My father was an orthopedic surgeon, so he was not impoverished, but his attitude was very much formed by this idea of poverty and pride, and not having much respect for people like the surgeon in San Diego that he thought was out of line. But anyhow, he came back to Lima. Now, Hoosier, we're told, was attached to citizens of Indiana to distinguish them from their Yankee neighbors. And When he came back, he actually taught chemistry as a resident in Lima. He taught chemistry to the nursing students, and one of those nursing students was my mother. So these were, I was so lucky to have these parents. My mother, the Yankee, her mother, although much poorer than my father's family, was the accompanist for the Lima Choral Society. So these were the Yankees were a more cultured set of people. And my dad was quite busy as an orthopedic surgeon, so my mother really raised me more than he did, and I think more of what her culture rubbed off on me than his. Both of them campaigned very vigorously for civil rights and got recognized for it locally. This is me in 1944. And there I am 5 years later, by which time I had two brothers. I remember just at this time, when I was in third grade, or maybe it was fourth grade, having my middle brother John there and my cousin Mary, the same age as John, sit at desks in this living room where this photo was taken while I taught them a lesson. So this was my first teaching that I can remember. Now, northwestern Ohio is rich in agriculture. This is the farm of my mother's, where my mother's grandmother was born, 8 miles from Lima. I was a city boy. I grew up in Lima. Lima had a population of 50,000 then. I think it's a little less now. Lima had a lot of important commerce. It was the Lima oil field was the biggest petroleum producer in the world in the 1890s. But closer to my time, they made steam shovels, lots of heavy industry, the biggest steam locomotive that hauled coal through the Alleghenies, school buses, and Cadillac funeral coaches, among other things. I think none of these exist anymore in Lima, except there's still a Standard Oil refinery there. Actually, it's BP now, I believe. So here's Lima. And I didn't live near the center of Lima. We were way down in the southwest corner. So when we came back from Sioux Falls after the war, that's where our house was, down in the corner there. And there were 5 other houses that had been built about the same time in 1929, 1930, roughly. But there were a lot of other small houses around from people who had come back from the war. But there were no kids my age. The kids of the new people, there weren't any kids in the other yellow houses there, and none any place close to my age in the other houses. So I did a lot alone until I went to elementary school 3/4 of a mile away at Roosevelt Elementary School. I needn't say that it's Theodore Roosevelt, not Franklin Roosevelt. I met friends there, and these friends I still have, the ones that are still alive, and we had a lot of fun. But actually, we spent a lot of time reading. Of course, what we read, and this is certainly part of my intellectual trajectory, was comic books. I had subscriptions to 2 different comic books that I remember. This is from that one. And an interesting thing here is what at the time. Science was very respected in the popular culture. When you had an ad for something to reduce stomach acid, there was a guy in a white coat and so on, and he did experiments for you on the TV. So although I had an uncle who was a chemist, but no one else except my father, who pretended to teach my mother chemistry. But I'm sure there was an important subliminal message at that time that science was a good thing to do. Actually, I thought I would be a doctor, probably like my father and grandfather. But I read a lot of other things besides comic books. I read a lot of books. I'm sure they weren't good books. I don't remember many of them. I remember reading all the Dr. Dolittle series, because a bookmobile would come and I'd get a big armful of books and take home for the next week to read. That's probably the reason I got the least coveted award in my senior year, which was most studious. I actually brought it to show you here. It's on the mantle.
That's totally funny.
But I had a job as a page in the Lima Public Library. I didn't think about it at the time, but I'm sure one of the reasons was that the librarian was my mother's aunt, Martha Gamble. And as I prepared this talk, I suddenly realized how much influence she had on me, both obviously through this job, but also because in her home she had such great things to see. For example, leaves of medieval manuscripts like this 14th century missal from Rouen and so on. And she had great taste, which I didn't recognize at the time, but I'm sure it had an influence on me. So anyhow, I graduated from Lima Public High School and went to the College of Worcester, 125 miles away. I had two friends that went to Harvard at the same time, two of my closest friends. But I didn't even think about going to Harvard. The only place I applied was Worcester, partly, I suppose, because I was Presbyterian, and still am. But there's a library at Worcester also. It was built in 1906. And in the reading room, there were things I hadn't really been exposed to yet. If you look around the frieze at the top of the reading room, there's Copernicus, Raphael, Demosthenes, Michelangelo. I assume Angelo is Michelangelo. I don't really know. And Calv, do you have any idea who that is? Calvin, of course. And Lavoisier, the chemist. They had a wonderful chemistry program. And Moses. And Darwin in 1906. In 1923, Charles Wishart, the president of Worcester, fought the forces of fundamentalism in the Presbyterian Church and defeated William Jennings Bryan in the campaign for moderator of his General Assembly. So Worcester was, people who aren't exposed to it wouldn't know, but it was really very, very respectable, and I loved it there. I loved it in part because of the president, Howard Lowry, who was a very wise man. One of his sayings was, "There's no college that's not the best for someone." And I think Worcester was certainly the best place for me at the time, and the best place for a lot of people. He was a great public speaker. I really admired his talks. At one commencement talk, he said at the beginning, established a rule for commencement speakers: realize that not all you say will be heard. But I had much closer contact, of course, with my teachers, like Francis Giel, professor of French. Shown here with François Truffaut, who made the story L'Histoire d'Adèle from her edition of Hugo's daughter's diary. She was a real crazy person, as you may know, especially if you've seen the movie. But for me, the most important influence, perhaps, when I was at Worcester, well, maybe chemistry, but certainly second was Miss Giel, because she led a study trip on French language and culture to Paris after my freshman year, and I went along. Part of the time I was just a tourist, like interacting with the pigeons in Trafalgar Square here. But once we got to Paris, I actually lived in a garret, because I was the only male in this group. There were 17 females and one male, so I always had to have a single room. So for a month I had an actual garret room in Paris, and this was a real eye-opener for me. But the other professor who had the most influence on me was Ted Williams, who was the first African American to be a faculty member at Worcester, perhaps the first to reside in Worcester. I'm not sure, but he was actually a wonderful man, and he was a good chemist, but he was a great person. At his funeral about 10 years ago, there were more than 1,000 people in attendance, including the Emerson Quartet, who came and played voluntarily, who volunteered to come and play. He was a marvelous person, very interested in chamber music, and inspired me. And when I was thinking of going to Harvard, he looked things over and said that would be a good idea. So after 2 years at Worcester, I transferred to Harvard. I also had great interaction with the other students at Worcester. For example, he liked to say there's no limit to what you can accomplish if you don't worry about who gets the credit. But the other students there also had an influence on me, like Bill Rogers, another chemistry major, who passed on some wisdom he had received as a summer student from a Harvard student who was in residence in the summer. The Harvard student told me he was just goggle-eyed at Harvard, of course. But the student told him, yeah, at first you feel pretty small. But then you decide you're as good as the next guy. Maybe a little better. So this sort of harmonized with, I guess, the independent spirit of my Scotch-Irish ancestors, right? So I had a good time at Harvard, but not the same kind of time I had at Worcester. It wasn't nearly as interactive. When you walked by someone on the street, they didn't smile and say hello, for example, which everyone did in Worcester. But I did find a group that I interact. Oh, I was going to say this is something that happened at Harvard that never happened at Worcester. On election eve in 1960, a friend of mine from Lima went to the hotel where Henry Cabot Lodge was said to be going to appear, the VP candidate with Nixon. But he never showed. So instead, we went over to the Boston Garden. And this picture appeared in the Boston Globe the next week, which is me shaking hands with JFK on the eve of his election. And times were different. Look at my left hand. I've got a coat over my arm while I'm shaking hands with Kennedy, and no one's thinking twice about it. Isn't that amazing that could happen? Anyhow, that was fun. But the group I found that I really acted with was at the Memorial Church, not having anything to do with religion, or not very much to do with religion. It was the university choir. And John Ferris was a sublime choir master, director, organist. He was a great guy. But even more important for me was the star soprano, Florence Stapleton. And within 6 months of our first date, we got married. And that's been the real core of my life since that time, of course. But I took courses at Harvard too. So organic chemists at Harvard thought of themselves as educators, like Louis Fieser, who's shown here, who taught the organic course, elementary organic course I took the year I transferred. He had written lots of textbooks, and they'd have things like this in them, which don't look very interesting either to you or to me. But what I found really fascinating was the footnotes. He had 537 intellectual trajectory footnotes, right? For example, this one was to himself. Louis Fieser, born in Columbus, Ohio, got his PhD at Harvard with James Bryan Conant, taught at Bryn Mawr and then at Harvard, right? So he studied with Conant, and I think most of you have heard of Conant. And he did a lot of thinking about education, but at a pretty high level, not at the sort of direct encounter with students kind of level. But his mentor as a graduate student was Elmer Kohler, who really thought of himself as an educator. Of course, he did lots of important research too. But the thing I like about him was that in his whole career, 30 years at Harvard, he only went to one meeting away from Harvard. Right? He thought his job was at Harvard, teaching people, both graduate students and undergraduates. Okay, so these were organic chemists. But the next year I took physical chemistry. Conant said about organic chemistry, we may rest confident that the fascinating art of organic chemistry will yield only slowly to the devastating inroads of an exact science. And he was right about that. But times were changing. The next year I took physical chemistry with the guy on the left there, George B. Kistiakowsky, a very distinguished physical chemist who had just returned from being Eisenhower's science advisor, the first science advisor to the president. And for some reason, he seemed to think that teaching physical chemistry to us was not quite as interesting as advising Eisenhower. In the first lecture, he said that we had a textbook and that it talked about thermodynamics. Thermodynamics was quite straightforward. We just read that in the textbook. He wouldn't lecture on that. He would lecture about quantum mechanics, and as a result, I didn't understand either of them really for years and years. But Conant was key in this because he did two theses, or a two-part thesis, and the other was with a physical chemist who became his father-in-law, T.W. Richards, who was the first Nobel laureate, first U.S. Nobel laureate. And Conant had another graduate student, Paul D. Bartlett, who because of Conant's interest from both physical and organic chemistry, put them together. So Bartlett was sort of the father of physical organic chemistry, using the precise tools of physical chemistry to study questions that had to do with the behavior of large organic molecules. So this is Paul Bartlett, and he taught the course I took, the other course I took as a senior. Actually, in my spring semester, my senior year, I had a straight. His course, which I just loved, I got an A. Kistiakovsky's course, I got a B. Another course, I got a C, and another course, I got a D. But I was already into graduate school, and I had an NSF fellowship, so that's fine. So, at any rate, the course I took with him was absolutely eye-opening and fascinating, and very different from Fieser's course, the elementary course that I'd taken the year before, which had a lot of anecdotes and stories in them, a few of which turned out, later I found out to be true, but not very many. Mostly they were just good stories, right? And I loved his stories. I loved Kistiakovsky's stories. But Bartlett told the truth about things, right? And our textbook was Mechanism and Structure in Organic Chemistry. That is, how are atoms really arranged in organic molecules, and how do they move around as you react from one thing to get to another. So this was a very different approach, and one that really resonated with me. When I was ready to go to graduate school, I decided that just at this time that I wouldn't go to medical school but go into physical organic chemistry. And I asked Gus Mackey, who was a physical chemist at Harvard, and one of my teachers who had gone to Berkeley. I applied to Berkeley and Harvard. I asked which I should choose, and he said in physical organic chemistry, Harvard is king. So I stayed at Harvard and worked with Bartlett, of course. This is a festschrift for Bartlett where there are pictures of lots of molecules he made to study carefully important theoretical points. And one of them here I'm going to show you because it was related to what I worked on as a graduate student. A molecule like this that has those nitrogens in the middle with a double bond between them, if you shine light on it, it knocks the nitrogen out. And you get these two things called free radicals with broken bonds, so single electrons, whereas bonds, as you probably know, come from two electrons interacting with one another. Now these electrons are magnetic, and they line up in a magnetic field or with respect to one another, and they can be parallel, but if they're parallel, they can't form a bond. And if one of them turns over and becomes anti-parallel magnetically, then they can form a bond, right? So an important question in dealing with such things is how fast can they turn over and form a bond once you've made it? So that was the question I wanted to address. So the question is, how can you measure to get a number for the rate of which the electrons flip and bonds form, when all you could observe is the product? You can't observe this directly happening. You have to do the reaction, see what the products are, and somehow infer from that what happened in between. Right? So my idea was that you do competition with molecular rotation, because there are ways of estimating how rapidly a molecule can turn over in solution. And if we knew how fast bond formation was compared to how fast it could turn over, then you'd have a way of estimating how fast they can turn over. Okay? Or how fast the electrons can turn over. So this is called cage coupling of the free radicals. So this is in benzene solvent. So there are benzene molecules rattling around the molecule of interest that I made. And if you shine light on it, you can break those two bonds and get the nitrogen molecule, and it goes away out into solvent someplace. And you have these two that can react with one another, right? But we want to know how fast they react with one another. So if we look at this sort of from the end, we can see one of these radicals with three different things on it, and on top of it another one, right? And they can move around relative to one another until they get close enough that they can form a bond, and you get a molecule that looks like that. But you could have exactly the same initial arrangement and move it around, but on the way, flop that thing over. And then if it continues and form a bond, you have a different product. So by telling the product, you can tell whether it turned over before it formed a bond. Right? So if it was very slow to form bonds for these electrons to turn over and form bonds, then you'd expect a lot of randomization and to get 50-50 of these two products. But if it was fast to form a bond, then you should get mostly the way they originally were relative to one another. Now there was a problem, because there's another product that could form. You could transfer a hydrogen from one of those two radicals to the other and get these two molecules instead of either of the dimers at the top, right? Fortunately, that only happens 25% of the time, so it looks like we're golden. We'll do the reaction, we'll measure how much of these two products we'll get, and I'll be done with my thesis. Okay. Now, at this time, there was an interruption while I came down to Yale to do my job interview. This was just before Christmas in 1966, right? And then I came back and resumed the thing and found that it was 50-50. It was completely randomized, and this didn't seem right. So I put a compound called a thiol in there, which has a hydrogen that's easy to give away to things. I found I got none of that stuff. But none of that either. It was all the other product. And the reason was that that hydrogen can be given to these radicals and form that stuff. So they didn't react with one another at all. They got apart from one another. And this question of rotation relative to one another was absolutely a nothing question. Right? So, at this stage, I had the job at Yale, but I didn't have a thesis. Right? So the reason was, with these three large groups attached to each of the carbons with an odd electron, coupling is too slow to occur within the fluid cage. They just get apart from one another. So this was a situation of panic. But if you get lemons, make lemonade, right? So I tried something else. I have to make these react with one another, not get apart. So what do? I think you could think it out too, even not under the same gun that I was, which is you make it in a solid instead of in solution. So they can't get apart from one another. Now, of course, you have no idea how fast things turn over in the solid. The whole premise of the thesis, what we were going to study, is completely shot. But I have the molecule in the way of doing the thing, so I'm going to try it in a solid. And I found that if you froze the solution before you did it, then the things coupled without rotation. It went from 100% rotation to 10% rotation. So I'm finding something about how easily molecules turn over in the solid. Right? And furthermore, it favored that hydrogen atom transfer the other way. That was only 25%. At room temperature became 60% if you froze it. So suddenly my interest changed from how fast the electrons turn over to how reactions in solids differ from reactions in solution. And in fact, if you look around the room here, you see lots and lots of organic molecules. For example, Dan Rosner here is an organic set of organic molecules. Reactions are happening in these things, many of them not desirable. But they're not happening in solution. They're happening in viscous or structured things. And the rules might be different. So it's worth studying how things react in solids. At least that's what would get me a thesis, right? So until this time in the 1960s, almost all information about the behavior of short-lived molecular fragments, like these things with just one electron, had to be inferred from the nature of the ultimate stable products, the way I just described to you. But we had just gotten in the chemistry department at Harvard something that Werner knows well, electron paramagnetic resonance spectrometer. This was, I think, the first commercial one by Varian. So we wanted to try and see, maybe when I froze this thing and knocked the molecules apart, because this thing will see only molecules that have one electron like that, the odd electron. It won't see any others. So even though there's almost none of it in there, a part in a million or something like that, still you'll be able to see that and nothing else. So we tried it with this molecule that I had. I froze it, benzene, to get a polycrystalline powder and photolyzed, and sure enough I got this signal that said I had it. That was after 2 days, and after 9 days it was practically the same. These things would last forever at liquid nitrogen temperature, these things that are very, very reactive with one another in solution. But the best luck I had was my roommate, Jim Vincent, because he actually worked in electron paramagnetic spectroscopy. He was a physical chemist. And he said, why don't I do it with a single crystal? Right? So I tried it with a single crystal. Now, what's special about a single crystal? Well, here's a statue of Benjamin Silliman out in front of the chemistry building. And if you look at his hand there, that's by John Ferguson Weir, incidentally, for those who what he's holding in his hand is a single crystal. And this is amazing. I never thought this way before. When you hold it, this single crystal is made out of molecules, right? So in the middle of it, there's a molecule, right? And if I go like this, I'm looking at different sides of that molecule. I can look at any orientation of that molecule I want to by manipulating the crystal. It's like a clamp on the molecule, right? So I tried a single crystal of this stuff, and if I had it, put it down in this magnet, right, and put it like that at 0 degrees, then I'd rotate it 10, 20, 30 degrees, so I could get one line or 3 lines or 4 lines, or as I rotated it through 180 degrees, all different patterns, looking with the magnetic field at different directions with respect to these free radicals, as they're called, the things with odd electrons. Okay, now if I plot this at different angles of rotation of the crystal going up and down and the position of the lines, you can see it's not random, right? There's a very definite pattern there. And that provides detailed structural information about these intermediates that you could never see in solution because they wouldn't last nearly long enough. But from the maximum splitting there, the maximum separation of lines, you can measure the distance between those two within a precision of 1% of a bond length, right? And if you look at what angle that's measured at, that tells you what direction there is between these two radicals, right? So within 1 degree of orientation. So you can find the precise structure of these reactive intermediates and actually see them, right? Now at this time we came down to Yale, and that's how one dressed for apartment hunting in New Haven at that time. And then I painted the ceiling and went back to Cambridge to snowbake and type on my thesis. And finally, we got here just in time. And it was a hectic time, but Flo and Toby were sources of sanity. Now, shortly after I arrived in October, a description of my thesis work came out in Chemical and Engineering News, which was good news, except that my name wasn't there in the byline. It was only and I was somewhat taken aback by that. But in the next month, there was a letter to the editor called Credit to McBride, and it said that the unauthorized deletion from the byline of the words "and James Michael McBride," that no notice was given of this extraordinary action and no proof sheets were provided. I'm embarrassed that my coworker, who not only did all the experiments but conceived most of them, was deprived of the recognition to him. So in fact, I came out ahead in this thing by Bartlett giving me all the credit for it. But I had wonderful mentors here at Yale as well. Phil Lyons was the chairman who hired me, and I think most of you know or knew Harry Wasserman, who was non-pareil. But closer to my area, Ken Weiberg and Martin Saunders and Jerry Burson were all physical organic chemists, different from me because they worked in solution and I worked in solid, which had quite different techniques. But here at Yale then, physical organic chemistry became king because by that time Bartlett had left Harvard. So this was a real golden age for us in this field here at Yale. We have wonderful students and postdocs. This was my group at the earliest time, and the fellow in the middle, Don Malamant, and I were helped by Hal Wyckoff in MB&B, who I knew as a fellow of Berkeley College, who taught us how to do X-ray diffraction. So with X-rays of single crystals, we could find out how all the molecules were oriented and packed together in the initial crystal. And then with our technique, with EPR, we could see where the fragments were. So we could know the detailed structure of the surrounding and how the pieces would be moving inside to react. Now, just 2 years earlier, the there was an important series of 10 papers about solids. Not many people worked on solid-state organic chemistry, but these guys in Israel, Cohen and Schmidt, had a paper called Topochemistry, where there were, of that compound on the left, there were 2 different crystal forms, alpha and beta, and they gave completely different products, and no one understood why when it was photolized as a solid. And what they showed by X-ray was that the neighboring molecules in the crystal are arranged in different ways, and they react with minimum motion in order to. So, as Jack Dunitz at the ETH said, everything fell into place and order had been created out of chaos. So here were some people that weren't doing exactly what I was doing, but were very interested in the kind of thing I was interested in. And then I met Meir Lahav, who was postdocing in Bartlett's lab at Harvard when I went up to visit one summer after a Gordon conference. And he had come from that group in Rehovot in Israel. And through the rest of my career, he's in a sense been my research director. He told me what was interesting to do, and I did it. And it was really so wonderful. But he started by saying that within 2 months there was going to be the second international symposium on organic solid-state chemistry in Israel, and I should go. So he gave me an outdated announcement of it, and it said, "It has been decided to emphasize the following topics: reactions in organic solids, right, and spectroscopy of molecular solids, both things I'm working on. And plus I'd get to meet the organizers, Schmidt and Cohen, who were interested in this kind of thing. Now there was one problem, that it was scheduled for September 14 to 18, 1970. You may not know it by those dates. It came to be known as Black September. Do you remember Black September? On September 1st, the cholera epidemic broke out in Jerusalem. On the 7th, the Popular Front hijacked and blew up Swiss Air, Pan Am, TDO, and BOAC planes. And on September 15th, Hussein attacked the PLO. And on September 18th, Syria attacked Jordan. So there was a lot going on. But what I focused on was not that. Flo, I think, focused on that. But I focused on meeting people like Clyde Hutchison from the University of Chicago, who was an EPR spectroscopist and had done things in single crystals too. And he, in a talk there, said that he thought of a crystal as a molecular ring stand, just what I've been taught, something that would hold it and allow you to look in different directions. So he was a big influence on me too. Before I went, there was a question of how it's a problem to communicate to people in an audience or in a paper how all this pattern is arranged. So we actually made this model of plastic and so on, and I put it on a rotating bookshelf and took a Super 8 movie of it while rotating it to give. So now we can do Kai, You're So Kind, but I could never tell the story I'm telling without graphics like we have available in PowerPoint now, but that was how I did it then. And it was quite clear to John, our son there. Now I want to show you just the kind of stuff. So here's a molecule that you can photolize, shine light on, and break out 2 CO2 molecules and leave 2 of these things free radicals, long chain things, right? Now, we could do X-ray and tell how far apart those 2 red atoms are in the starting material. And we found that when we photolized it, we got the radical pair, and then another radical pair, and another radical pair. They're the same radical pairs, except they've moved a little bit, and we can follow their motion using this technique. And finally, they come together and form a bond. So, for example, we can measure the distance between them, which I show there. But I'll plot it here. The remarkable thing is that they're going to move together, but first they move apart, and then they come together. So why do they move apart? Right? Now, bonding distances between atoms within molecules are about half as long as non-bonded distances. So if you took that molecule in the middle, and there's a bond distance, and there are non-bonded distance to adjacent molecules. Right? But if you break the bond, now you have 2 molecules there, and they're way too close to one another. So there's going to be enormous local stress, high pressure there, that's going to force these things apart. And in fact, we could study that kind of thing in 3 dimension and find exactly how these things move. First, that curved arrow, 1 carbon moves there. Then at the other end, the other carbon moves, and we could tell not only where the first carbons went to where the second carbons originally were, but the second went to where the third was. So this zigzag chain had been pushed and rotated 180 degrees and just backed up by one zig. So we could tell all this thing, which no one else had been able to see for details of a reaction like that. And here's the same thing seen from the top. Right? But how about, is there really this pressure in there? Could we measure it? And we were able to measure it, what the CO2 pressure was, because we're generating CO2 right between these things. But so using infrared spectra, we can show this. And you can see that as they move apart, as the radicals move apart, they back up, the pressure falls, that highest frequency peak moves down and down. And we could measure that the original pressure on the CO2 was about 40,000 atmospheres, so quite a high pressure to move these things. Now, I said that as I say we did it. Actually, who did it was Mark Hollingsworth, and he did hundreds and hundreds of runs in a single day. A single run would take 3 days on this, so he'd sleep at his machine. But in the long run, it paid off. This was his thesis, Infrared Studies of CO2 Dimers as a Probe of Local Stress in Solid-State Reactions. But that's just one volume. In fact, there were 3 volumes, 1,078 pages, and he got the American Chemical Society prize for the best PhD thesis in the U.S. that year. He also got some other prizes for the thesis. But so we were looking in great detail at these things and trying to get the worm pulled out. And of course, what you find when you do this kind of thing often is that there's more than you expected. And I'm just going to click through this real fast to show you, so we can see that break apart 2 CO2s. That moves down to there. Then this one breaks apart over here. Then that one tacks there. And that one takes that one, and you get that, and then that moves up there. And these are different intermediates. So there you see, you break it apart. There's 1, 2, 3, 4, 5, 6 intermediates. But if you put a deuterium atom, which as Werner knows you often do to simplify the spectrum, you find that it actually changes the reaction. It goes there. And if you put it a different place, it goes there. And if you put it a different place, it goes there. And another place goes there. Another place goes there. Another place goes there. So there were 10 intermediates on 7 different reaction paths in this. And this was just getting to be too much. It just says, by God, for a minute there, it suddenly all made sense. And the only person that made sense to was the graduate student who did it on the right there, Mike Buer. And that was the most rococo job we ever did, I think. We also studied high energy explosives decomposing in this way. But the other 2, the women in this picture, especially Jen Swift in the middle, changed our perspective. We weren't going to be able to go any further than something as complicated as that. But what was often a challenge to us was to get the crystals in the first place. And Peter knows from X-ray crystallography of biological molecules that getting a crystal is often a big barrier. So we began to study, instead of reactions in the crystals, the crystal formation or dissolution as a reaction itself. So we were able to resolve a 19th century puzzle about what were called optically anomalous crystals, and also gave very pretty pictures. And we used a new technique called atomic force microscopy, which you will understand. I have difficulty explaining this to students.
You will understand?
You will all understand what my students wouldn't understand, because you know what a phonograph machine is like, right? You put a needle down and you move something underneath it and it goes up and down, right? It feels the surface. That's what this is, except that the needle is very, very sharp. Right? And the amount of motion it's sensitive to is very, very small. So this is part of a crystal. The width of this scan is 1/6 of the thickness of a human hair. And those little holes that I'm going to show you in the middle are about 1% as wide as a human hair. Okay, so they're very small. And what we see here, if you were standing there and looked around you at this topography, right? What you would see is that you're on a flat plane, right? And there's a pit 3 steps deep there and a 2-step pit to the north, because I scratched a little bit with the needle, right? And here's a high cliff. When you look to the northeast, there's a bunch of layers going up, and atop the cliff there's some single stairs going up, and down in the lower left there are 2 steps going up. So we're down in a trough here, right? But there are these 2 pits. Now, a step here is 1 molecule deep. So we can tell when 1 molecule's thickness goes away. Right? We don't have that resolution laterally. The smallest holes near the X there are about 800 molecules wide. But the height we're exquisitely sensitive to. So now we can watch as we put solvent on it, and it begins to dissolve. The things move back. So look at the next step here, and you can see that it dissolved fast, very fast in that way, fast there, slow there, and very slow. So according to the structure of the crystal, these things move at different rates, and we can use this to find out why things grow at a given rate, why crystals have the shape they do. Right? So here we'll look at it. You see they grow. But look at this one, though. That pit is not growing. So this pit that's 800 molecules wide hardly dissolves at all. And if we do it again and scratch deeper here, there's 11 steps there and 12 steps there. But let's focus on the very smallest pit as the others are dissolving away. And what you see is that it fills in. Right? While everything else is dissolving, this one fills in. So the crystal is both dissolving and growing at the same time. And this has to do with a phenomenon which had been thought about a lot theoretically, but I think not observed well, which is the idea of a critical size, that if it's big it'll grow, if it's small it'll go away. But really the most interesting thing maybe has been undergraduate teaching. I was part of the team that developed in 1991 Perspectives on Science, which made science for freshmen at Yale more like science was for students at Worcester, where you got to form a community with people and do research. But also in 1972 freshman organic chemistry. Now I have just about enough time to finish here. Freshman organic chemistry. There was a freshman physical chemistry being offered to outstanding students who were coming into Yale to try to draw them into the chemistry major. But the organic chemists got together and said, organic chemistry is so much more interesting than physical chemistry. Wouldn't it be better if we had a course of freshman organic chemistry? So they asked me if I would do this, and I was happy to do it. And the idea was to get more chemistry majors. Right? Well, that didn't work out so well. Of the 35 students, 4 became chemistry majors. But they were really, really special students. Like Evan Kozlau, who was in the first fall semester of the course, said, after I had been talking about that if you spent enough computer time, you could calculate anything as accurately as you wanted to. So Chaim Pekaris had recently calculated the energy states of the helium atom within an accuracy of 9 significant figures. Right? So really, really precise. And Evan asked, how is that possible when the mass of the electron is known to only 6 figures? I just asked John Tully at lunch today, a National Academy member. You may know John, who's a really hotshot theoretical chemist. He said, I have no idea. So this was a little, this was not going to be a standard class. I've looked back at the careers those 35 went into: academic medicine, practice of medicine, chemistry, other science, law, business, others. And there's some impressive people, like Steve Benner was the co-author of the Woodward Report. There was a thing in the alumni magazine you may have seen this month about the Woodward Report, which talks about he wrote the first draft and Van Woodward revised it. So when he was an undergraduate, and he became an assistant professor at Harvard, then a full professor at ETH in Zurich. And then he established a thing called the Westheimer Institute for Synthetic Biology. So he applies organic chemistry in really amazing ways to biology. And David Agard, who's a professor of biochemistry at UC San Francisco, he's a HHMI investigator, a very prominent guy. Barbara Beer, who became president of professor of medicine at Harvard and vice president for research at Brigham and Women's Hospital. Howard Hoekstra, I don't know if any of you might know him. He's a professor now in medical school here. John Burt is professor of English American literature at Brandeis. Jay Blumenthal was the Microsoft program manager. He's the guy that headed the team that developed Excel. Right, but then he became a high school science teacher, and now he's a climate and land conservation specialist in the Northwest. The question came to me, what should I be teaching these people? Right? They're not going to care about the details of organic chemistry, right? But at precisely this same time, our son turned 3, just in the second semester of this course. There's John McBride, age 3. And for the next 365 days, 15 times a day, he said, "How do you know?" Right? And it occurred to me that is the question that the people should be asking. How do you know these things? Don't just tell them the stuff. Tell them how you know it. Right? So there are 4, this is a little piece from my course, 4 ways of knowing. Right? So here's a Carolingian manuscript or illumination. So here's Moses getting the word from God. So one way of knowing is divine authority. And down below he tells the students, right? Human authority. Right? But science isn't faith-based. Right? We don't count divine authority and human authority. Not that they don't exist, but they don't exist in science. Okay? But we have a lot of respect for experimental observation. And so the freshman organic course, as far as I know, is the last course at Yale that requires lab. Right? Taken simultaneously. Because you don't get the right idea of what science is if you don't take lab with it. And logic, of course. So then, how do we know about organic molecules? By feeling. With like this needle in the atomic force microscope. So this is what I start my course, or when I was still teaching it, what I started my course with was these things of how do you really know these things, and teach them how an atomic force microscope works, how how X-ray diffraction works, there's this picture that Rosalind Franklin took at DNA. How do you look at that crazy thing and know that it's a double helix with major and minor grooves? So we would talk about that in the course. And then calculation. Chemical quantum mechanics, not the whiz-bang stuff in physics, but how do bonds work, and so on. And we did really rigorous, but not quantitative quantum mechanics in the course. And this turned out to take about half a semester. But the really interesting question after going this to look at the most modern stuff, all of this is 20th century, and much of it is the 1990s, right? No chemist was surprised when people used these high-powered tools to figure out what molecules looked like. How could they possibly have known without these tools how atoms were really arranged and moved around, right? So we went back to see why they weren't surprised. So we did history. How did the chemical ideas really develop? Not peeking behind the curtain with X-ray and so on, but how did people figure it out? So we shifted emphasis from how chemistry works to how our understanding of science develops, something that will apply in all sciences and all aspects of life. Right? So I over the years, I looked at a lot of things, generally moving back in time. First, about the first observation of trivalent carbon with something with a bond broken, which was by Moses Gomberg in Ann Arbor at 1900. Then how atoms are arranged in space, how you could get information of that without actually seeing them, by Vatoff in the Netherlands. Then the first really rigorous proof of a structure, which was purely, which could be formulated group theoretically. So I worked with George on that, George Seligman. And then how Archibald Cooper erroneous theories of organic chemistry. You can learn as much from erroneous ones about how science works as you do from the real ones. About Lavoisier and Davy, about theosophy, and that was my millennial contribution, was about theosophy. Then finally I moved back to being most interested in Restoration London and science there, especially Robert Hooke. So teaching Chem 125 involved many responsibilities, such as countless lonely hours spent grading Chem 125 exams, or supervising preliminary lab work of a future freshman organic student, now a professor of biology at Bowdoin. This was my office. A student showed this to show students at my retirement due. A student put that up, so I showed a picture of my office now. Actually, our son made us a coat of arms at home. McBride, Hik Ali Kubi. It's haystacks, one of which has a needle and a little pica below. Here somewhere or other is what that means. But then we have these two granddaughters who are so great, and we love to work together.
There's another piece in this piano that is actually designed to muffle the string, called dun dun dun, the damper. I will use a pillow pet, a croquet hammer, and a telephone pole wire to show you how the damper acts. This croquet mallet is acting like the hammer, and the telephone pole wire is like the strings. When I hit the string with the hammer, it vibrates and makes a small sound. To make the sound stop, I put the damper, the pillow pet, on the string. The dampers are normally on the strings to keep them quiet, but two things can lift the damper. The first one is the keys, which lift a damper as long as your finger is on the key. The second one is the pedal, which lifts all the dampers, but otherwise works the same.
Okay, that's Katie. This is Annika. She drew this picture. I think that this girl is working with chemicals, it says. But this is her on the scientific method. Annika, I really like your new bicycle.
How do you know?
So I think the future's in good hands. This is just the beginning. Thank you. I'm done.